and welcome to Enough with the Science. I'm Senan.
And I'm Joe, and welcome to another half an hour filled with crazy quantum stuff.
Actually, Joe, why don't you introduce this week's topic? We'll reverse the roles for a change.
Absolutely. Like, we talk about many, many big topics here, but now we're talking about very, very small things that have very, very big implications, but not on a practical level.
Yeah.
So we're talking about quantum states.
Yeah, we're talking about the weird states of matter, most of which are down to the quantum weirdness, quantum physics and all that. So this is part 2, of course. Last week we did part 1 where we...
That's the normal order of the things. We do part 1 first. That's good.
As you pointed out in the past, except in the Star Wars universe.
Yes.
Anyway, first off, because we have a lot to cover this week, so we're going to rattle right into it, is something called Bose-Einstein condensates.
Okay, so basically what we're looking at, though, are weird things that happen at the quantum level. Is that essentially?
Kind of, yeah. I mean, they're kind of weird states of matter. So when we force matter into a state...
A corner. When you put matter in a corner, nobody puts baby in a corner.
It does really weird stuff when you force it into a corner. Anyway, Bose-Einstein condensates, a theory came up with by 2 gentlemen, one of whom was very famous for his wild hair and a few other things.
And not the speaker dude.
And the other guy is not the guy who invented speakers. He is Satyanendra. I've murdered it.
Yes, you have.
Bose.
How much practice you need to get this right?
I apologise to his relatives who no doubt are listening to us for murdering his name. But anyway, he and Albert Einstein, they came up with this theory together that something called a Bose-Einstein condensate could exist. But it was many years before it was actually proved in a laboratory that it did exist.
They probably didn't call it a Bose-Einstein condensate.
I
imagine that would be very egoistic.
Yeah.
Egotistic?
Yeah. Well, I mean, we know some people some person that likes naming stuff after himself at the moment.
Oh, yeah, to be a lot of that, yes. But I don't think Bose and Einstein were those.
They were humbler.
They were humbler than that.
So I know at some point in this conversation you're going to ask me what the hell is the point of this. So I'm gonna get my retaliation in early. Yeah. Probably the most fundamental use of this otherwise useless thing is it gives scientists a glance into the hidden world of quantum waves, because normally all that quantum wave activity and stuff that's going on at the microscopic, in fact much smaller than microscopic level, is not visible to our laboratory equipment. I
have to say now, I'm slightly disappointed in you, Senan. Like, surely it's worth having knowledge for knowledge's sake. We don't need a practical application.
Well, of course,
they found this theory. They looked at the world. They used mathematics, and they went, "Look at this. This is the way things work." And then it was proven in a laboratory. How long? 40, 60, 100 years later. That's astounding.
I kind of feel like I'm being beaten with my own stick here. Anyway, right. Unfortunately, we need to delve into a little bit of physics theory before people will grasp what the Bose-Einstein condensate is. Right. There's a phrase called a quantum state, right? And it's like, we're talking about these subatomic particles now, quantum particles and so on. A quantum state is the complete description of all its properties. So things like how much energy it has, how much momentum it has, how much spin, which is like an angular momentum thing, what its position in space is, and so on.
Okay, now, so these things are atoms, or these things are smaller than atoms?
They could be atoms, they could be protons, they could be neutrons, they could be electrons.
So it's properties of any of those little
They could be quarks.
Yeah.
Right. So, but all of these things have a quantum state, which is like the list of all their properties, right?
Yeah.
Okay. Now, the reason we mentioned that is because there are 2 families in all of this particle soup that matter is made up from. These are just categories, right? Every one of these particles will fall into one category or another. There's just 2 of them: bosons and fermions. Bosons are named after our friend Mr. Bose.
Einstein.
Einsteinions. No, they're named after our buddy Mr. Bose.
What was his first name again?
Are you going to force me to insult his family yet again? Anyway, you can look them up on Wikipedia. And the difference between bosons and fermions is that bosons are sociable and fermions are not.
Okay, that's a good description.
So bosons are very happy to share the same. A bunch of them together are very happy to share the same quantum state. So all that list of properties like momentum and speed and all that stuff that we mentioned a moment ago, it's a bunch of bosons are very happy to all be in the same state, all have those same set of properties, right? Not the case with fermions. If you have a bunch of fermions together, they must all have a different quantum state. None of them can have the same quantum state. It's called the Pauli exclusion principle, and we'll be talking about it some more later.
Oh, good.
And it is a very fundamental aspect of physics. In that, so for example,
so Pauli exclusion principle only applies to fermions.
That's right. Yeah.
Okay.
Yeah. It's just the description of the fact that fermions won't all occupy the same quantum state. They have to be different. So I'm just going to give you a very quick digression to explain one of the fundamental. Although this is nothing to do with Bose-Einstein condensates, but it's just giving an example of how this exclusion principle of fermions actually affects things in the real world. As you're probably aware, atoms arrange themselves into shells around a nucleus.
No.
You might think of it as orbits. So,
there we go. Yes, that's better.
In physics, they're called shells, but think of it like the orbits of the planets. So Mercury is in the closest orbit to the sun. That'll be the near shell in towards the atom. And then Venus is in the next shell out. Then Earth is in the next shell out after that. Mars is the next shell out, and so on, right? So it's just like the orbits of the atoms. And the reason that happens is because the atoms are being forced to jump. So each shell has a higher energy level than the one before it, right?
Okay.
And the atoms, because no two atoms can occupy the same, because electrons are fermions. So no two electrons can occupy the same quantum state. So some of them are forced out to a higher energy level, which puts them into a higher shell.
Okay, so if you have like an atom with several electrons, they're all in different shells.
So some atoms can share the same shell because they're not in the same position, right?
Oh, no, but the electrons, though.
Or electrons, can share.
Okay.
Apologies, I'm saying atoms when I should say electrons.
That's always been a problem for you.
So imagine if Mercury had a partner planet that was around the opposite side of the sun from it, but in the same orbit.
Okay, that's possible.
So it's the same kind of thing with atoms, but there's only so many of them will fit into one shell because of other forces that are keeping them apart from each other. Right. So that's a digression. Let's get back to Bose-Einstein condensates. So what do? They take a gas made from bosonic atoms, so atoms that are bosons, because some atoms are bosons and some atoms are fermions, right? But they take a gas made entirely of boson atoms and they cool it down to almost absolute zero, like we're talking about the barest fraction of a degree amongst...
So bosonic atoms, it's like a secret organisation. Bosonic atoms, they could be any element. It's in a particular state.
Whether an atom is a boson or a fermion, is determined by the number of electrons, neutrons, and protons that are in it. There's a formula that you can use with those three things: the electrons, protons, and neutrons. And depending on how many of those it has, it will determine whether it's a boson or a fermion. In other words, whether it's happy to share the quantum state of its neighbours or not. Right. Okay. Mm-hmm. So in this case, we're talking about bosons, the guys that get on with each other. You've got a gas made from them, and you've cooled it down just a hair above absolute zero. What that does is it removes all the motions from those. So the heat is what gives those particles their motion, their movement. So you get them down to what's called their ground state, where all their motion is gone because you've taken away all their heat. And because they're bosons, they all drop into the same quantum state then. So they all act as if they're a single boson. They don't become a single atom, but they act at the quantum level as if they really are a single atom. And instead of them all having their own individual separate quantum wave, all of which would be infinitesimally small, their quantum waves merge and they create just one big quantum wave that spans across the entire bunch of gas that you've got.
Okay.
And that allows scientists to observe quantum activity at a larger scale where their instruments can actually detect it. Whereas normally it's at such a small scale that nothing can detect it.
Okay.
So by forcing the gas into this state, it allows them to observe quantum things happening.
Okay. I'm kind of getting it.
I kind of feel like there's a question coming after the okay.
No, I mean, I'm desperately trying to think of a question, but I'm just imagining this I don't know why, in a red plastic bucket, and like at the bottom of the bucket, there's a really thin layer of stuff that was all different a while ago and is now one thing.
Yeah. And it's called quantum coherence. When they all coalesce into that standard state. So I'm going to give you an analogy that might help people to understand it. Imagine...
Not me, but people who are listening.
Imagine synchronized swimmers in a swimming pool. And they're not synchronized. They're all swimming in their own different way. And you're an observer looking at them. You can't really see any pattern into how they're swimming. But suddenly, if they all become synchronized swimmers, all doing the exact same thing, you can clearly see what the pattern of their swimming is.
Okay.
So that's kind of the thing that's going on here with BECs, they're called, Bose-Einstein condensates.
Okay, you could use BECs for the rest of the episode.
Weirdly, they have, I do not understand how this works, but they have allowed scientists to slow light down to almost stopped. So light normally travels at 300,000 kilometers per second, but when they pass light through a Bose-Einstein condensate, they can slow it down to almost stopped.
I wonder the guy who discovered that, like, he's there in the lab going, lads,
there's something,
look at this.
There's something wrong with this camera.
There's just what's the speed of light again? Can we just have a look at this?
Yeah. And there's a few other, like, esoteric laboratory experiments that they make possible that you wouldn't be able to do otherwise, that we're going to move on from now, because that's enough about BECs. We're going to talk, and believe it or not, in comparison to what we're going to talk about next, for me anyway, Bose-Einstein condensates are relatively straightforward.
Right. Because if this is anybody who thinks that that's relatively straightforward, keep listening. Everybody else, come on, we're going for coffee.
Right. Super solids. These are deeply weird, in fact, mind-bending as far as I'm concerned. And again, it's one of these things which there was a theory developed around about 1970 that maybe these might be possible, that these might exist, but it was only 2017 before somebody actually managed to do it in a laboratory, and it's like really complicated
I wonder, was it like 10 years of absolute ridicule for the person, 1970. Guess what I've discovered?
I wouldn't be one
I don't
bit
think so.
surprised.
I don't think that's possible.
Yeah,
no.
That kind of thing has gone on in science an awful lot. Yeah. So yeah, I wouldn't be one bit surprised if they got that kind of reaction when they suggested it. Anyway, the key thing about super solids is the material they're made from is both solid and a superfluid at the same time. We spoke about superfluids last week. Now, just to clarify, it's not that it's flicking over and back between solid and superfluid and
ice.
back to
It's
solid.
not like you have an ice in a bucket and it's kind of, and then you're refreezing it.
Yeah,
no.
And it's not that some of it is solid and some of it is liquid. It's all of it is both solid and a superfluid at the same time. So imagine a sponge which has, water soaked into it. Well, imagine instead of water, what the sponge is, the liquid that's soaked into the sponge. Is sponge. Yeah, so sponge is flowing through itself. Like, it's just mind-boggling. I can't picture it.
The abyss. It's the abyss. It's them dudes that came up from the bottom of the abyss and came into the ship with the faces, the liquid, aliens. Yeah. They're super solids.
For those people who are under 40, The Abyss was a very good science fiction movie that was back out when we were young. Who was in it?
We were young, please.
Who was in it? Was Michael Douglas in it?
No. I can't remember. I can see the girl's face, but I can't remember her name.
Sharon Stone?
No.
Anyway.
Yeah.
Never mind. We'll be here all day.
We'll be doing our film podcast next week.
It's the understanding of it. We're very much at early days. It's been proven under.
Oh, yes, we are very much. We are pre-early days here.
I mean, it's been proven in laboratories that it exists, but I don't think anybody. It's a bit like I just made unobtainium. And speaking of unobtainium, we are going to move on to time crystals.
Oh yes.
Now, I've been struggling with trying to find a way to explain this that makes any sense.
You mean all the rest of that was clear to you? Wow.
Well, at least most of the other stuff I can create some kind of picture in my mind of what it might be. I'm probably a completely erroneous picture, but at least I do have I'm grasping something in my mind.
So now we're going to attempt to explain something in the podcast that you don't have a clear idea about.
No, not even a clear idea, even the vaguest idea.
At least you're being honest.
Yeah. Right, crystals. They're nothing to do with normal crystals. Time crystals, right? So normal crystals are things like salt or ice or metal or lots of other substances that are crystals, right? And what defines a crystal, as we mentioned last week, is the atoms are all lined up in a grid. So there's a kind of a lattice that they have all attached themselves to, and they're in a very regular pattern. And, the pattern just keeps repeating through the material. So they're all locked into this grid position, right?
Right.
Time crystals, nothing to do with that.
Okay. You can just ignore that last 2 minutes.
The reason they're called crystals is because there's a concept I am only going to touch on, so please do not ask me questions about it.
Hold on, I've got a list.
In physics called symmetry. Now, there's two aspects to it. There's translational symmetry in space and translational symmetry in time.
Now,
Right?
I know all about this.
You do?
No.
Please, I was looking forward to a break from speaking. I'm getting hoarse here. Please explain it to me. So anyway, a crystal, basically an ordinary crystal like ice or salt or whatever, without me going into too much detail, you love when I make that phrase.
It's my favourite phrase.
It breaks the physics concept of translational symmetry in space because the atoms choose to be in particular places in the grid, in the lattice that has the crystal held together, right? Whereas amorphous matter, that's not a crystal, the atoms don't choose to be in particular places like they do with a crystal, right? Translational symmetry in time is what a time crystal does. And it's basically...
Just say that again.
Translational symmetry in time.
Oh, God.
is the concept behind time crystals, right?
Okay.
Very briefly, certain substances that are in certain conditions, when you cool them down to absolute zero, so all the energy is gone. Those particles should not be moving anymore. You've taken by making them cold, you've taken away all the energy, like we said a moment ago. But yet, they don't do that. They start oscillating. So if you look at it now, it's in position A, the particle. If you look at it a second from now, it's in position B. A second after that, it's gone back to position A. So these particles start oscillating between two positions. And it's like they're choosing a moment in time to be one way and a different moment in time to be a different way, even though there is no external energy which should be permitting them to do that. They shouldn't have the energy to do that, but yet they'll do it in certain circumstances.
But are they actually moving between the positions, or are they just popping between the, like, going, I'm here, I'm over here, now I'm here, now I'm over here?
I don't know whether there's an actual journey taking place or whether we're in one place one moment and we're in another place a moment later.
It would make no less amazing.
Yeah, it would, yeah. But the point about them is that there's no external energy going in at all, which is normally required to make particles move. But yet these things will just go tick-tock, and keep doing that forever as long as you keep that material cold.
So why can't we use them for energy?
Because it's a locked internal system. We can't. It's different from, say, a quartz crystal, right, in a watch. You know, quartz crystals are in watches.
No, no, I don't.
So every electric watch or every electric clock, the way it measures time is by the oscillation, the vibration of a quartz crystal, right? Quartz crystals vibrate at a very specific frequency that we know.
So a quartz crystal, is a crystal.
Yeah,
it's also a time crystal.
No, it is not a time crystal, even though we are using it to tell time. I knew we'd get wrapped up in knots with this one, and we don't have the time to stay with it.
If we had a time crystal, we could get through this. But
anyway, the point about quartz crystals is because they vibrate at a very specific frequency, we can measure that and then use it to calculate how long a second is, and that's how an electric watch works, right? The only reason that quartz crystal is vibrating is because we're putting electric current into either side of it. So we've connected it to a battery, and that's making it vibrate. If we disconnect it from the battery, it stops vibrating. Unlike our time crystal friend, not connected to anything, has no external source of energy, shouldn't have any internal energy left, and yet internally its particles are oscillating between two positions. So it's a weird one that very few people... the theory only came about in 2012 by a guy called Frank Wilczek, who was a Nobel laureate, that it might be possible for this to happen. And it was only a few years ago, 2016, I think, 4 years after his theory came up, that somebody finally managed to do it. But they had to create a really exotic set of conditions in a laboratory to actually do it. But yeah,
palm trees and sand.
Yeah, and pina coladas. Anyway, we're going to move on to quark-gluon plasmas. So we spoke.
I actually don't think we should have a single podcast without quark-gluon plasmas in it somewhere. Just to be able to say it. Quark-gluon plasma. Quark-gluon plasma.
Do you know, it's actually easier to say than the acronym QGP.
QGP's got it, yeah.
Anyway.
It should be. It sounds like one of those things that people in the theatre should use to prepare before they go on stage. Quark-gluon plasma. Quark-gluon plasma.
Before they go out and do Hamlet or something.
Yes.
Anyway, we spoke last week about the fourth state of matter, which is like a normal plasma, which all the stars and the sun and lightning and everything are made from, right? This is a different beast altogether. But it's the way you create it is kind of similar in that normal plasma, when you add enough heat into a gas, the electrons gain enough energy from that they can break away from the nuclei of the atoms that they're normally orbiting around.
Right.
So they're kind of gone off on their own, the electrons, right? That's a normal plasma. A quark-gluon plasma, so protons...
I love we've got to the stage of this podcast where that's normal. That's the normal plasma. Now we're on to the crazy stuff.
So protons in the nucleus of atoms are made up of quarks and gluons, right? The quarks are like the building blocks, and they are glued together by the gluons, which are effectively what they call the strong nuclear force. It's the strongest force ever detected in nature, is the strong nuclear force, when they calculate the strength of it. And as a result of that, you never really see quarks outside of protons. They're always inside as a building block. They're never outside on their own running around, except in a quark-gluon plasma. So if you keep adding heat until it becomes a phenomenal temperature of 4 trillion degrees Celsius. I don't know about you, but that means nothing to me.
Well, I mean, the person who came up with it is like kind of not 3 trillion, not 3.5 trillion. We need 4 trillion degrees.
It is a bit specific, all right. It's about 250,000 times hotter than the core of our sun, so it's pretty warm. Anyhow, you've now given the quarks enough energy once you get to that temperature that they can overwhelm the strong force. They can actually break away, a bit like the electrons broke away a long time ago. The quarks are now able to overcome the strong force and break away, and suddenly you've got this soup of free quarks that are outside protons swimming around. Right?
Yeah, well, I imagine there's no protons.
No, the protons have been deprotonized.
Yes, they've been dequarked.
However, we'll never, as humans, ever, there's no chance whatsoever we'll create this in the laboratory.
And this is one of the very few times on this podcast where, Senan is 100% sure of
certain.
Something. Absolutely certain.
Yeah.
This is never going to,
Yeah, go down to the bookies now and put money on it.
Right? Never going to happen that we're going to get to 4 trillion degrees Celsius.
It's theorized that it happened for a brief fraction of a second just after the Big Bang. Like less than a second after the Big Bang, all of the matter in the universe was in this together in this tight ball, like pinhead sized probably. And it had so much heat at that point that for a very brief fraction of a second there was a quark-gluon plasma. It cooled. By the time a second had elapsed, it had cooled and we were going back to normal protons and normal matter.
Well, or they were there for the first time, surely.
Yeah, they were there for the first time, we would imagine, because we've no idea what happened before the Big Bang, so maybe they were there before the Big Bang, who knows. Right.
That's another episode.
We're going to move on to our last topic, and this is to do with what happens when stars die, all right?
Happy topic to end on.
And what happens when a star dies really depends on the size of it. Right. So if it's greater than maybe 2.5 times the size of our sun in terms of its weight, its mass, it's probably going to form a black hole. If it's a bit less than that, it's probably going to form a neutron star, which is what we want to talk about. We're talking about neutron degenerate matter here. So you kind of have to understand what's going on with a star. You've got 2 competing forces that are balanced, right? On the one hand, remember, stars are really, really big.
Gotcha. Finally, I understand something. I'm going to write that down. Stars are really, really big.
Yeah. In fact, you could probably use a third really if you wanted to.
Okay.
So, for example, our sun has more mass in it than absolutely everything else in the solar system combined. Like the sun is much bigger than all the other stuff in the solar system, right? And the more stuff you have in one place, the stronger the gravity. So you've got this really strong gravity trying to squeeze it into smaller and smaller space. Just its own gravity. But you have already squeezed it enough for fusion to start. Now, we did an episode on fusion there a while ago, so I'm not going to go into that. But anyway, the energy or the pressure that has been caused by this gravity squeezing has ignited fusion, and the fusion is creating outward pressure. The energy produced by the fusion is creating outward pressure, and you've got this fine balance between the gravity squeezing in and the energy pushing out from the fusion, right?
Yeah.
That's all
it's a fairly active spot, the sun.
Yes, that's all very well until you run out of fuel. And it runs out of fuel.
Which is very topical at the moment.
Yeah, it certainly is. It runs out of fuel more or less instantly. Like 1 minute it's there, the next minute it's not. And suddenly gravity wins and the star undergoes a massive collapse. A really violent, sudden, fast collapse because the fuel of fusion has run out. There's so much violence involved that the electrons, which should be orbiting around the nucleus of the atoms are forced into the protons that are in the nucleus. So you have electrons that bash into protons, and when they merge, they actually become a neutron. So what was an electron and a proton bashed in together, and they form a neutron, right?
Okay.
You've now got a situation where practically all of the matter, or most of it anyway, that was that star is now just neutrons. Nothing but neutrons. It's a really weird state of matter. Like practically every other form of matter we know, you have electrons, protons, and neutrons together forming atoms. Here you've just got a pile of neutrons, right? And they're really squished in dense together. You're talking about, like, it collapses down in size quite a lot. Like our sun is hundreds of thousands of kilometers in diameter. But if it was,
no need to be specific.
If it was to turn into a neutron star, it would only be about 20 kilometers in diameter. So all that material gets squished down into a very, very small space. Incredible density. Like if you could find a teaspoon strong enough and lift up a teaspoon of it, it would weigh around about 6 billion tons, which is about the weight of a mountain.
On a teaspoon. A mountain on a teaspoon.
Yeah, a mountain. Now we need to go back to our friend that we mentioned at the start of the show, the Pauli exclusion principle.
Look at that. It's almost like he's planned this.
So neutrons are fermions. So that means they won't all occupy the same quantum state. So the ones in the middle are that first become neutrons in the middle of the neutron star, maybe they're going not very fast, right? But the next layer out is forced by the exclusion principle to go a little bit faster, because if it didn't, it would be occupying the same quantum state as the ones inside it, right? So the next layer out must travel a bit faster.
So in order to avoid being in the same quantum state, they increase acceleration.
Yeah, speed, yeah. The speed they're traveling at, yeah. And as layers and layers and layers of neutrons build up away from the core of the neutron star, each layer has to travel faster than the one before it.
So, like, now I'm imagining, because initially when you said the star collapses, I just saw this big, dense, black thing, like solid thing there. But it's all whizzing at unbelievable speed.
Now remember, we are talking about subatomic particles here.
Yeah.
So, like, their motion is probably random in all kinds of different directions.
Okay, right.
So
it's not like whizzing, or you're not going to see...
It is rotating for a different reason, but not because of the motion of the neutrons, right?
Okay.
The different reason it's rotating is because practically every star system we've ever observed is rotating. So the planets in our solar system are rotating around the sun, and the sun itself is rotating in the same direction, right? And it's the same pretty much with all stars. So when you collapse the diameter of the star that maybe was rotating at, we'll say the star was rotating at 100 kilometers an hour, right?
Yeah.
If you collapse that big, huge diameter of a star down to something that's only 20 kilometers, it accelerates the rotation. So yes, they're spinning really fast,
but
not because of the neutrons.
Okay, right.
Yes, yeah. As I say, as the layers of neutrons are building up, each layer is getting faster and faster and faster, right? Now, earlier on, I mentioned that if a star was like more than 2.5 times the mass of our sun, it's probably going to end up a black hole. The reason for that is that eventually you reach a point where the outer layers of neutrons are being forced to travel at the speed of light. Okay?
Which is not possible.
Which is not possible, right? And it means that the Pauli exclusion principle is overcome by the speed of light. So eventually you break the Pauli exclusion principle, and that causes the whole thing to collapse into a black hole.
Ouch.
So that's neutron stars. I mean, they're pretty amazing. And here's an interesting Irish connection. So there's a particular class of neutron stars called pulsars, right?
Yeah.
And they are spinning very fast, and out of the poles are these beams of intense radiation, like a laser beam, like a pencil pointing out of each north pole, south pole of the star. And a lot of them would be, as well as spinning, it'd be wobbling a bit. And that would mean that some of them, the beam would briefly sweep across Earth. And it does that because the thing is rotating at a very specific constant velocity. It sweeps across Earth maybe once every 3 seconds.
Like a lighthouse?
Yeah, like a lighthouse, maybe once every 3 seconds, bip, bip, bip. And that's how they became to become pulsars, because they were reliably hitting Earth for a moment every minute or every minute and a half. Every pulsar has a different interval. And it was
the time would be longer than... No?
So it depends on, like, some of them are spinning ridiculously fast, hundreds of times per second.
Okay.
So the time varies quite a lot. But an Irish lady, Jocelyn Bell Burnell, a physicist, discovered pulsars. She was in one of the universities in Britain. I think it might have been Cambridge. But yeah, she was the one that discovered pulsars. So it's nice to have an Irish connection at the end of our story. That's the end of our tour through weird and exotic states of matter.
You really enjoyed that.
Well, look, quite,
No, but I mean, like, you normally enjoy the content of the podcast, but it's when you get to the very edge of what we can understand that you get completely animated and go, look, I have no idea what's going to, like, I'm going to try and explain this.
Isn't it pretty amazing, though, all the stunning things that are happening in the universe that are so far beyond our understanding?
What amazes me is that, like, mathematics leads to so much of it.
Leads
to all the little symbols and pluses and minuses and entire, like, books full of this, and they can decide that at, like, a very fundamental level.
Like, for me, the genius of those guys like Einstein is they had a blackboard full of equations, and they're able to draw conclusions from that. They're able to say that mathematics means that this physical thing must be happening. I mean. Yeah. That's pretty amazing to me. Like, and
then, like, to have people to go out and go, okay, I'm either going to prove it or maybe disprove it. Maybe they set out to disprove it and then went, oh, wait a minute.
Yeah.
But like, they actually went out to try and do it.
I'm sure there's physicists that several times have said to themselves, oh no, Einstein was right again.
Yeah. I don't believe it. I do not believe it. Well, we hope you enjoyed that little trip through the crazy states of matter.
Yeah. That's enough exoticism for one podcast, I think.
Okay, so thanks for listening. I'm Joe.
Yeah, and check us out on enoughwiththescience.com. I'm Senan. Goodbye.